So we introduce the dot product initially in order to figure out angles between vectors, but then it's really so simple. As you can see, that formula is really addition and multiplication followed by addition. So that angle at the end is really stand in the way. It appears that as if it's just equally important, but it's really not. So this is my definition. Really simple, and we're going to use it all the time. In fact, to emphasize that point before we move on, if you don't feel like doing it by hand, well, that's what Excel is for, and Excel actually has a function that does exactly that. So it's worth mentioning. Whatever. So I have a bunch of values here, say 1. Okay, so that's my like 7-dimensional vector. Okay, and I have another one. Okay. Okay, and then so nothing. That's all there is. I have 2 8-dimensional vectors, and it might be I can compute the dot product between them as very simply. There's a special function. It's called not dot product. It's called sum product, I believe. Sum product, indeed. Okay. And all I have to do now is I have 2 arrays. One array, or I think let's do one array, comma, the second array, here, come on. Okay, that's it. Right, so it does exactly what we do by hand. Sum product means literally multiply pairwise like this. As long as the 2 arrays have the same size, they will multiply by one, and then the results are added together.
So
okay, so
1 multiplied by -3 plus
2 times 2, 3 times 3, 4 times 8, so on. So that's all there is. Okay, and then since we're not entirely, we don't want to limit ourselves to only that, we can now let's do that. Let's compute the angle. So it is a 2 8-dimensional vectors. Let's compute the angle between them. Okay, so how do we do it? Right. So we normalize the dot product. That's right. So we're going to need the two. Norms. So these are the vectors. So vectors, and then over here I'll put the norm. Norms meaning the magnitudes. Here. Okay, so these are the 2 vectors, say, I don't know, A and B. Okay, so I will put magnitude here. Once again, I could do it one by one. It's not hard, but since this has a function, the same function can be applied. So I do sum product again. Sum product of an array with itself. Comma, and then I do it the second time. Okay, so in other words, it will be multiplied by itself, and that will be my, except I forgot the square root. We need the square root here. Okay, so take another look at what I'm looking at. So array, those 8 numbers, multiplied by itself pairwise, that's what sum product is, and then square root. That's the norm. Okay, 6, 6. Yeah, seems reasonable, does it? Yeah. So it's hard to develop an intuition for a spaces this high dimensional, as a matter of fact. Okay, so let's do the other one quickly. Okay, 9. Okay, and okay, so and then for the angle here, I will put angle here. So this one is dot product. This is dot product, and here I'll put the angle over here. So what do? I take my, as was pointed out, I take my, well, first of all, it's going to be our cosine, right? So a cosine, a cos, our cosine, okay, of what? Of our dot product divided by the product of the two magnitudes. So that's, in case you don't remember, this is the formula right there. So a dot b divided by norm a dot norm b, okay? So so I'm going to be put this one here divided by parentheses this times that, two parentheses, I believe. Okay, does it look okay to you? I have no idea what the answer should be. Okay, so so this is in radians, obviously. So was it 0.68 in radians? What is it?
1 radian is equal to
Pi 3. So it's
so
1/5 pi roughly. So it's fairly narrow. It's a small angle. Okay. Actually, a more interesting question would be to look at angles between, what is the angle between two basis vectors? Two basis vector meaning,
122.
what?
122.
What's 122?
This one. If you convert it
To, well,
degrees.
let's convert it to degrees. So this is equal to this divide by 100, multiply by 180, right? And divide by pi.
Oh, you said.
39 degrees. Yeah, so it's less than a quarter. Yeah, seems reasonable. Okay, actually, the more interesting question is, what is the angle between two axes? That seems obvious, right? By construction, it's 45 degrees, right? And no matter what dimension is, two axes by design have a 90 degrees angle between them. But what if we will look at them instead of as vectors, and we'll look at the average? So the question I'm trying to answer is this. I'm not missing it. And that still did not want to do it. Nope. Sometimes just something's happening here. Incomprehensible. Okay, so the question I'm trying to ask is, well, to say that let's suppose E sub k is the kth basis vector. In other words, it is the unit vector in the direction of kth axis. Okay, so this is E1, E2, E3, that's dimension 3, and then there are more. Okay, so the angle between, well, first of all, it's very easy to see that E k dot E, say M, is equal to 0. I mean, after all, the first vector is made of a bunch of zeros, and then with a 1 somewhere in the middle on the kth position. Okay? And then I'm multiplying it by the same thing, only this time the 1 is at the position M. Okay, so these are two basis vectors, and that's what they made them basis. Not basic vectors, but basis vector, because they form what we're going to call a basis. So so what happens then there's only one component of this vector, of such a vector, is non-zero, depending on the axis, so kth position or mth position, and so the product is what? If k is not equal to m, what's the dot product? So many zeros. It is 0, right? So that, because k is not equal to m, there is a mismatch, and you have the whole thing is 0. So which means that they're perpendicular. Okay, unless it's the same vector, they're perpendicular. But what is an interesting question to ask and to explore the n-dimensional space is, what about the average? So I take 1 over n E1 plus E2 plus En. So in the two-dimensional case, it's simply the diagonal. This is what I'm talking about. And in dimension 3, it will be pointing at us, also a diagonal. Imagine over here I have a rectangle or a square and the diagonal. On the left, in three-dimensional case, I have a box. And once again, I'm looking at the diagonal, a box, a square box. And I'm looking at the diagonal, so once again, a vector. It is actually a unit vector. You see that is a unit vector, right? Because there will be exactly, well, you can actually tell what the coordinates are. 1 over n, 1 over n, 1 over n times. So it's a unit vector. Okay, and then well, let's take a look at what happens with that with just direct computations. So suppose I'll make my a unit vector, and I'll make my b that diagonal vector. So it will be made of 1/8. It's a dimensional thing, so a 1/8. January? Really? That is silly. Okay. Look at that. 1/8. Okay, that's better. Down. Hold on. Why is it not a unit vector? It is 1, 2, 3, 4, 5, 6, 7, 8. Hold on a second. It should be divided by, wait a minute, by square root of 8, not by 8. In order to for it, I just jumped to conclusion. That was just too quick. No, wait a minute. 1. No, hold on a second. N times 1. No, it's not square. Hold on. Why didn't it work? Maybe our formula was wrong entirely. So this works out. 0.13. Why is it not?
What makes something a unit vector?
A magnitude 1. So that's why I'm surprised. Magnitude should be equal to 1.
Okay.
So 1/8. Yeah, okay, yeah, it's divided by square. Wait, hold on a second. 1 divided by... Okay, so it's a unit vector. Okay, so and the angle is 69 degrees. I'm not sure what oh, okay, so 69 degrees instead of 90, instead of okay, so everything is fine. So it's diagonal vector. I'm computing the angle between the diagonal vector and one of the unit vectors, one of the basis vectors, right? So A is the basis vector, and this is the diagonal vector. The answer is 69 degrees. So what does it tell you? Compared to the situation that we can actually handle, dimension 2, dimension 3, the angle in the case of dimension 2 is what? 45 degrees, right? So you start with 45 degrees, then it appears that the angle what's happening is growing. So there seems to be more room between those vectors. So it's like you can already see that you can already see if you look at that angle, the diagonal, that angle has higher angle. That vector, the orange one, the diagonal one, has higher angle with the sides than 45 degrees, right? You see it? No? Well, imagine, look that if you look at the corner, okay, so forget about the basket, at the corner, and imagine there is a vector or just a rod going from that corner in our direction, like this. Okay, and now think about what angle it forms with the, say, the corner, that corner.
So this line will go towards you?
Yeah, so these are the three axes. I'm trying to reproduce the picture that I have on the left.
Can you show
Like that one, yeah.
Yeah, okay.
Can you show with the ruler? There's a ruler right there.
No, I don't see a ruler.
It's right here.
Okay, yeah, okay. So, yeah, so what I'm talking about is this, like this. So it's a diagonal, the average between those three. So imagine a box one by one, and then you go diagonal.
Yeah.
So what is the angle? No.
Oh, angle of what?
Of this and that.
More than 45?
Yeah.
Wait, listen.
You don't see that it's more than 45?
I mean, it's like closer to that line, so it's less than 45, right?
It is closer to the ground than to this.
I mean, you're showing like this, so I'm assuming.
Well, I guess.
Okay, then it's more than 45.
I guess my demonstration is not as convincing as I hope my mathematics is.
Then if it's closer to this plane.
Yes, then to the vertical direction, right?
Yeah, then
Yeah.
it's like.
Right, but do you see why it should be?
Yeah.
I wish we had an actual box. You don't have a box. So it's not, doesn't sound convincing, I suppose. So a box, one by one, and one by one, okay, and then the diagonal within that box, which points at, that's not a good box. Well, let's say which one I'll pick. Maybe I'll pick this one. It's a bad box. I don't like it. Let's start over. Okay, so a box. Okay, like this. Okay, this is a box. Oh, it's a box. So what I'm talking about is from this one.
45?
No?
Why not?
So that's what the math say. Don't you see? Well, let's build up a little bit more stuff here. Okay, so so what is this angle over here? It's 90 degrees, right?
Yeah.
9 degrees. This is 1, right? This is what's the other side? The square root of 2. What's the red one? What?
2,
No.
1.
What's square root of 3? Right? 1, 1, 1, square root of 3. Okay, so we don't really have to do dot product if your dot product is not convincing yet. So that's a triangle. So any complaints or questions about this? So it's 1 by 1 by 1 cube. And we're looking at this triangle. We're looking at the diagonal, which is the length of which is square root of 3, right? Okay, and then the diagonal at the bottom is square root of 2. It's simply diagonal of the square. The top is 1. Okay, so then my triangle is this square root of, this is square root of 2. This one is 1, and this one is square root of 3. Okay, so remains to be seen as, well, you can see that it's not 45 degrees already. It's not 45 degrees, right? So the angle that we're concerned with, this one, is not 45 degrees, and you can see that it is smaller than 45 degrees, right? Because, well, I mean, you can actually do cosine. I don't think you can solve this problem without trigonometry, but cosine alpha is 1 over square root of 2. Wait a minute. It is 1 over square root of 3. 1 over square root of 3. Right? Okay, so rather than 1 over square root of 2, it is 1 over square root of... That's a sine. Square.
So how do you know the bottom?
Oh, hold on a second. It's this...
Root 2 root 3?
I missed. It's square root of 2 over square root of 3. Okay, that's the formula. I messed up really, really badly. Okay, so, okay, I'll let you do it. What's the formula?
Root 2 root 3.
That's right. Okay.
Do you need to multiply?
No, you don't. All I will try to prove is that this is less than 45 degrees.
No, I mean like in the denominator.
No, this is trigonometry. This is not the dot product. So I just did trigonometry from, high school definition of cosine, and since this is the only thing that you might be concerned with is to compare 2 over square root of 2, square root of 2 over 2, I did it again, square root of 2 over 2, which one is larger? So to find out that angle, we know that it's not 45 degrees, but is it less than 45 degrees or larger than 45 degrees? All we have to do is compare these two numbers, and I think we can see what this is. Square root of 8 here, and square root of... What?
It's like 35 degrees, I think.
Well, I have 69. Why do I have 69? No, that's dimension 9. Dimension 8, rather. So why is it higher than 45 degrees?
Yours?
This one. Dimension 9, it should... Oh, okay, no, the other one. The angle that we looked at right now was the angle with the plane, not with the other vector. So you take that and subtract from 90 degrees, and so the degree grows. Okay? Right, do you get 69 degrees? No?
90 minus 35. We got 54. 54 something.
The angle that we found is this one. This is the angle that we found.
Then in our case it will be 54.
What?
54.
Well, you gotta trust mathematics at some point.
54 something.
No, it's possible. The point is that it's larger than 45.
Yes.
And it grows as the dimension grows.
Okay.
So in dimension 8, the difference is even more pronounced. It's actual the whole 69 degrees. And you can guess what's happening. It will actually go to, or it will be approaching 90 degrees as n grows to infinity. Okay, well, I hope we have taken care of this controversy. Yeah, so we had to do actually high school trigonometry because that visualization did not help. So anybody was convinced by the actual experiment?
Will you get me out of doing trig again?
Well, that's the thing. That product you don't have to do trig. The trig is all inside of the dot product.
Oh, okay.
It's not that you entirely free because, but I think you picked the right you picked the right linear algebra course, because this formula that we just had, it actually follows from law of cosines. Okay, so that certainly is, yeah?
So where you had the triangle on the other page we were just on, yeah, how do you know the bottom is root 2?
It's all 1 by 1 by 1, right? So it is simply the diagonal of a square 1 by 1, right? So 1, 1, 1, the Pythagorean theorem. And the diagonal was either, once again, doing a Pythagorean theorem again. Square root of 2 plus 1, square root of 2 squared plus 1 squared gives you 3. So the diagonal is the square root of 3, the other diagonal. Yeah. Okay, so this follows, just to finish this up, the formula that we're going to be using, if necessary, for the angles. Now, not really that usable as some others. It follows from the law of cosines. Then we also convince ourselves without proof that inequality at the bottom is true if what we're looking at is indeed cosine, that it is between -1 and 1, which means that there's this relation that seemingly has nothing to do with trigonometry, is that the absolute value of the dot product, that's what's on the left, the absolute value of the product, remember it's a number. On the right I have two vectors, and I have two magnitudes of them and multiply them. That's one thing. On the left I have the dot product, which is a number, I take the magnitude of it. So this is called the Cauchy inequality. Yes. Let me just... So it is on the fairly long list of properties of the dot product. Remember, so we have the algebra of the dot product. We want to match it with the algebra of vectors, right? So what happens to the dot product when we do algebraic operations on vectors, such as addition and scalar multiplication? So it's a very much same problem as we face when we introduced the distance in the dimensional space, and we had those properties. I remember, not too many, 3 properties. Remember, not a long time ago. Where are they? These are the ones. Okay, so on the right, I have my magnitude. I said distance magnitude of the vectors is what issue at the what's at issue, and then we saw how it combines with how it interacts with the algebra. So property number 2, one is very basic one. Okay, number 2 is about the scalar product. What happens with the scalar product when we take the magnitude of the resulting vector? And the answer is we simply factor a out, that scaling factor out. See over there on the right, and you just add absolute value. Okay, and then secondly, the triangle inequality. What happens to when you add vectors? Well, then if you add vectors, then versus adding vectors versus adding magnitudes. Well, as you see, you cannot have higher than that. Cannot have higher than that. But what really is so we won't have the same thing, but about the dot product. Okay, so remember these properties. Just put it in your mind. Okay, so this is solved more or less. An example. Okay, so properties of the algebra of the dot product, or well, just the algebra of the dot product. Okay, so the basic, let me just do what we already know, and that's the most important is this, the connection to the magnitude. So A dot A is equal to the norm of the magnitude of A squared. Okay, so that's the very first property, and then we at least we can figure out some of the properties of the dot product from the properties of the magnitude. Not too many, but at least there will be some. So well, let me do the property number 2, the property of scale multiplication. So if I do on the right, I do it C, right, it was A capital, okay, squared is equal to absolute value of A times magnitude squared, magnitude A squared. Is this clear, what I did here? Ignoring this. So this is property number 2. I use the property number 2 from the list of properties of the magnitudes, right? So the magnitude of A times scalar product of A capital, the vector, is once again A. The scaling factor is factored out of the magnitude with the absolute value attached. Okay, so and then we have squares. Okay, so and this is A dot AA. Okay, does it help at all? I don't think it helps at all. Yeah, I don't think it's really that interesting. Yeah. Okay, so let me start over. Sorry about that. I don't think it gets us anywhere. So this property, well, I'll just put it on the list. It's more of a kind of a property that you have at the bottom of the list. It's more complex property. It connects to some previous things. Let's do the scale multiplication combined with the dot product. So for example, A dot B. Okay, so as you can see, well, you see what we're facing here. We have 2 multiplications this time. So I hope it's not too intimidating just yet, but we have introduced one more operation. We already had 2. We already had scalar multiplication of vectors, and we had the addition of vectors. Now we have added the third operation, which is the dot product of vectors, which produces numbers. Okay, so what am I looking at here? I'm looking at this is what I'm looking at. I'm looking at the dot product of 2 vectors. A lower A. Well, I don't like that A here. Let me just put I don't know, X. Okay. So X is a number, A, B are vectors, and I take the scalar product of 8 and multiply dot product with B. The answer is, what is this, a number or a vector?
X times AB?
Well, right, yeah, that's what I'm driving at, but it is a number to begin with, and then secondly, so we call this, you already know the answer for well, you can say what you're trying to say. Did you say X?
Is it X times like the dot product?
That's right, X, A dot B.
Yeah.
So what do you call this? Associativity, yeah, so another associativity. Okay, so if it is true, obviously, but it is. Okay, so as you can see, we have another multiplication, 2 multiplications combined together. I intentionally put an X here with a dot there to indicate the dot product, and the other multiplication does not have a dot there, but it's still multiplication. So I don't want to do anything exotic here. You can just look at do it coordinate-wise. There's really no trouble whatsoever. Remember, what happens is that you multiply. This is the way you can write it sometimes. A sub I, and B is equal to B sub I. Okay, then XA is X AI is equal to XAI. Okay, so what is scalar multiplication if not simply multiplication of each term, each component of the vector by that number? So geometry is a stretching, right? But sometimes it's just easier just to do algebra coordinate one component at a time. So in each component, this computation will be carried out as I indicated. So A is equal to AI, which is the string of numbers. Each of them is multiplied by X, and then you have simply a string of X times AI, and that's the result. And then what I'm supposed to do is on the left, I'm supposed to multiply by this by B. Okay. So tell me what XA dot B is. We are multiplying XAI, one vector, and I'm doing dot product with the other one, which is BI. So what's the result? Well, what? Well, almost. What's missing here? It is the dot product, so what's missing? No? For dot product is the tricky part about dot product. That's the product, and there another operation. Addition. So okay. So as you can see, that's all there is. So that X at this point, what you're looking at it. What do you want to do? Looking at this expression, what do you want to do with it? You want to factor X out. Right, so because it's repeated, so you have AI, BI, okay, and what is that we're looking at? X is outside, and what is the summation? What is the summation this is? XI, summation AI, BI. What? Okay, yeah, it's simply the dot product of A and B. Okay, so we started here. We started this way. Okay, XA dot B, carried out the computation, factored, and we realized that we are back to dot product of A and B. Okay, so so that's the associativity. Now, what other properties would you like to have? Associativity, what else? What? Commutativity, well, yeah, absolutely, commutativity. A times dot B is B dot A, right? Commutativity. Right, because it's either way it is summation AI, BI in either case, or it is summation BI, AI, or this is the same thing. Okay. One more. Well, if you remember any names from distributive property. So since this is a new kind of multiplication, and we still have addition to worry about of vectors. So the question becomes what is it? What's happening? So this is the distributive property will be, I distribute A over additions. So it will be A dot B plus A dot C. The proof is once again is uncomplicated. So it will be this is summation AI BI plus CI, right? That's on the left. And then what do? I just distribute. I use the distributive property of numbers. These are numbers, right? At the last line, these are numbers, so I can just distribute this multiplication, and I have sum AI BI plus AI CI. Okay? And finally, I just split it in half like this. And I have come back. Right? Okay, so it's uncomplicated really. Dot product is defined in terms of the coordinates, components, and so we just as well we can do all the proofs in terms of the components. There are a couple of simple properties, or maybe just one. The one that we definitely need is 0 dot b is 0. So the 0 vector is special because it's all made of zeros, so you multiply component-wise, you will end up with 0. I don't think I've missed any, but let me just take a look just in case, so that I have all the properties lined up. Associativity, commutativity, additivity, okay, distributivity. No, that's pretty much it. Okay, so the point of the dot product was the angles, and what is the most important angle is 90 degrees. So it comes very handy to be able to rotate an angle through 90 degrees on the plane. Okay, so that's what I want to just quickly point out of what we have time left for. So what is A rotated 90 degrees counterclockwise? On the plane. Okay. So I have a vector A, and then what I'm supposed to get is this vector, which is A rotated 90 degrees, which is say B. You can do trigonometry, right, to find it, but with the dot product, it's much easier. So just you remember that the dot product should be 0. Okay. So if A is equal to A1, A2, and B is B1, B2, they're supposed to produce 0. A1 times B1 plus A2 times B2 is equal to 0. So can you think of vectors? You need to think of B1 and B2 that would produce 0 here. No, maybe. So A1, A2 are unknown and they are given. So I want the answer based on for any vector A ahead of time. So well, let's say, I don't know, 1, 2. 1, 2, and what is the other one? That would produce 0. Yeah, that is a good one. That's anything else?
Can it be minus negative 2?
Could be. Negative 2, 1, that's right. Negative 2, 1. So 1 times negative 2 plus 2 times negative 1 is equal to 0. Natural 1 over here. So in other words, you flip the two components and change one sign. Flip and change the sign. So the answer is, let me write it out. So B is equal to negative A2, A1. So from A, which is A1, A2, we produce a vector that is rotated by 90 degrees, I believe, counterclockwise. Yeah, so x was positive becomes negative, as an example, and the result is 0. So that will come very handy many times. Okay, so see you Friday. The homework will be assigned tonight.